We've all seen this before. To the vast majority of citizens in Canada, driving is second nature. All the motions fit together seamlessly. In terms of fine motor action and control, driving is the epitome of reacting to change in the environment by using our muscles to interact with the world. But driving is not just the simple, straightforward two-piece puzzle of stepping on a pedal and steering a wheel. When you are driving, you must also incorporate visual feedback of what is in front of you. This feedback comes from all sorts of traffic signs and stoplights, where different colors and shapes produce different cues for motor commands, changing the way you react in a motor capacity. From moving the wheel to putting your foot in the right place and applying the right amount of pressure, a lot of quick decisions need to be made. Using driving as a rough example, we can see that the intersection of visual, attentive, and motor information is important for movement. So, how does motor cortex encode this information and use it in an effective way? We will be answering this question by exploring a research article from 2011 produced by Eisenberg and colleagues titled "The Representation of Visual and Motor Aspects of Reaching Movements in the Human Motor Cortex." But first, we should get some background on prior studies and what we already know about related motor neurons.
The primary motor cortex, or M1, is located in the frontal lobe along the prefrontal tragus, and is one of the main areas involved in motor function. It has previously been determined that the M1 is responsible for encoding muscle force, direction of limb movement, and sensory motor transformations. It is also sensitive to targets positioned on screen, and 20% of M1 neurons display sensitivity to color. Eisenberg and colleagues, the author of the paper, have previously found through multi-voxel pattern analysis that M1 also conveys information about hand movement direction, and these patterns of activation have higher correlations during movements in a similar direction in comparison to those with less similar directions.
So we have a lot of information on the primary motor cortex, but there are still some important questions to be answered. If we know that M1 has a role in extrinsic coding, does that mean it is limited to strictly motor encoding, or does it involve attention and visual cues as well? In essence, is the primary motor cortex more versatile in the information it encodes? When visual and attentive information is important to motor movement, will it also be encoded with the motor info? In other words, when stimuli are context-sensitive to motor behavior, will they be encoded? The author's previous experiment found that M1 neurons were sensitive to movement direction. Now they want to know if this sensitivity is due to motor aspects of the task, such as hand movement, or visual aspects, such as target location or color. They are attempting to extend the understanding of the primary motor cortex neurons by demonstrating that visual aspects have an effect on activation. Given the previous research and what still needs to be discovered, the authors believe that activation in M1 during visually guided reaching movements carry information about direction of hand movement as well as visual elements of reaching.
The experiment starts with a baseline center-out task, with each trial lasting 4 seconds. Participants start by seeing a red circle in the center of the screen. After 500 milliseconds, 5 circles appear. 4 of them are blue and 1 of them is green, indicating the target. 2 seconds after the peripheral circles appear, the red circle turns into a white cursor. With the remaining 1.5 seconds, the participant must move the cursor towards the target. The circles will disappear once you reach the target, but they also disappear if you don't reach it in the allotted time. The rotation task follows, and it is the exact same breakdown as the center-out task. However, the cursor trajectory does not match the target, so participants have to rotate the cursor between 0, 45, 90, 135, or 180 degrees. There were 50 trials for each degree of rotation. Participants had a 10-minute practice period before this task to learn how to rotate the cursor. There were also intermittent trials that appeared. These trials ranged from 2 to 8 seconds long, and like the other tasks, a red circle as well as periphery circles appeared. However, the red circle did not change to a cursor, indicating that it was a null trial. To help interpret results, the researchers also included 2 more tasks. The first is the observation paradigm. In this task, 6 of the participants simply watched the cursor move for 125 trials. They then completed 250 trials of the baseline center-out task and repeated the observation condition again for 125 more trials. To ensure the participants were paying attention to the observation runs, the researchers had them rate the accuracy of the cursor movements for each trial. Finally, there was a task to localize area MT. In this task, participants were shown white rings at low contrast. The rings alternated between staying stationary and expanding or contracting. They were required to fixate on the center. What you are seeing here is an example of what the ring might look like.
23 people participated in the study and 13 of them were female. In order to be eligible, they had to be 18 to 35, be right-handed, and have normal to corrected vision. Participants laid in a 3T fMRI scanner throughout the experiment. In their right hand, they held a joystick which they used to navigate the tasks. As well, they used a mirror to view the tasks above their head.
The data analysis followed a few steps and occurred as followed. First, the region of interest was determined using the Brain Space Voyager QX, and the first two functional images were discarded. Head motion correction algorithms and high-pass filtering were applied to remove drifts and improve the signal-to-noise ratio. Using the Talairac space, the area of the brain scanned were transformed to ensure consistency. The functional criteria for M1 voxels was simply the presence of a higher bold activation during movement trials as compared to null or baseline trials, and voxels were included in the M1 ROI if there was anything within a spatially contiguous cluster. Beta weights were applied for each movement in voxel, and a correlation was calculated.
The resulting correlation coefficients across all participants between baseline and rotation sessions are seen in this figure. The motor selective voxels in the left panel, or the visually selective voxels in the right panel, are depicted in light gray bars. Dark bars in both panels show the original results using all of the M1 voxels. Error bars denote the standard error of the mean across participants. Notice the elevated correlation of the motor selective voxels in the movement matched condition. Similarly, a higher correlation is seen during the visually matched trials in the visually selective voxels, without a drop in the correlation during the movement matched trials. The two voxel populations, therefore, do not entirely overlap, nor are they mutually exclusive. This is a lot of information and a lot of fancy words, but don't worry, it'll make more sense in just a second. Using a deconvolution method, the time course of brain activation for all the voxels in M1 were analyzed. Based on the results, it was found that both motor and visual directional cues are in fact encoded in the patterns of activation across M1 voxels. What does this mean? It means M1 voxels likely contain genuine information about the visual components of the task. Further, it is worth noting that the positive correlations were seen between the M1 multivoxel patterns evoked by the baseline run and by the rotation run when the two movements were matched in their movement direction but their visual aspects differed. In plain language, this means that the activation does not differ based on what visual information is being conveyed. When visual elements are important to motor movement by cueing them, the information will be encoded along with the direction of limb movement. To summarize, the primary motor cortex is in fact sensitive to visual and attentive cues, but it is context sensitive. Visual information is only encoded when it is relevant to successful motor action. So we just gave you a lot to think about. Let's take a moment to discuss what all this information means.
Through this fMRI study, we are able to gather more evidence that the primary motor cortex is not just involved in motor processes. Rather, it draws on visual components to support the process of making good, precise movements. These cues are visual and directional, and the patterns of activation recorded in the study suggest that M1 is hard at work using visual feedback to make precise movements. This also helps us look at the brain more holistically. We know that the brain has functionally specialized areas, but the input to these areas involves many sensory modalities. Knowing that visual cues are encoded in M1, in some cases, lends support to the idea that the brain can also work as one unit. As with any study, there are limitations. Firstly, this is a region of interest study, which we know from lecture has its downsides. Secondly, the authors stated that a previous study showed that groups of M1 neurons start out sensitive to target location, but direction of hand movement becomes more important over time. Due to the temporal resolution of the fMRI and bold response in this study, this result could not be replicated. Additionally, poor signal-to-noise ratio resulted in an inability to replicate results of other studies, which found higher visual encoding in the dorsal premotor cortex. Finally, for future directions, the researchers indicate an interest in looking at individual neurons and seeing how this changes the results.
In conclusion, the researchers increased our understanding about the primary motor cortex by finding that both movement direction and visual aspects of a task are independently represented in regions encoding hand movements within M1, consistent with their hypothesis. This study allowed us to fill many gaps in the current literature. This includes the knowledge that activation in M1 during visually guided reaching movements did in fact carry information about both the direction of hand movement and the visual elements of reaching. Interestingly, however, The relevant visual aspects are only represented in M1 when directly coupled with movement, not when actions are passively seen.
So there you have it. The primary motor cortex incorporates more than motor commands and facilitates fine motor control. Although we should always interpret results with caution, this is a useful piece of cortex to have. Without it, it would be far more difficult to incorporate what we see into our movements, and we might find ourselves needing a different method of getting from place to place.